My name is Cameron Roberts. I was working on LiLi a few years ago and am now currently working on low carbon mobility at Carleton University in Ottawa, Canada. Okay, yeah, and what I've been working on quite a lot is, so I'll just get started right away. What I've been working on quite a lot is trying to sort of balance the fact that my current employer is a bit of a technophile with my desire to be a bit more critical about this stuff. So I've been studying a lot about the various high-tech solutions for sustainable mobility. And for this, I'm using one of the many, many acronyms that has been developed for basically the same concept of connected, autonomous, shared electric mobility. So the basically electric robo Uber as the solution for sustainable transportation. I'm going to present, this is based on largely a lot of literature reviews I've done, a few interviews, and I'm going to present some early ideas here. I'm trying to get some support to do some more detailed empirical work on this stuff, but I think what I'm trying to do at this point is raise some broad questions and try to frame the debate a little bit. One thing I want to point to is this picture in the background here of these these autonomous vehicles driving people around. Notice how 1950s looking this picture is. I think that actually says something, which I'll elaborate on a little bit. Anyway, I'm going to cover a lot of stuff here. I'm going to move fairly quickly, but I'm happy to return to slides in the questions. So, and if you want me to slow down at any particular point, please go ahead and ask. So, first of all, there's a narrative that has shown up a lot, right? I'm sure you've encountered it before. Here's Rethink X, a Canadian think tank. We are on the cusp of the fastest, deepest, most consequential disruption of transportation in history. Of course, it will still involve highways, but what it will evolve is autonomous vehicles, which will be electric, etc. We also see this from various online news outlets. Google's self-driving car will change everything. Here's a very popular YouTuber who is talking about how autonomous vehicles will solve all traffic. We got the McKinsey guys getting in on it. And of course, no discussion would be complete without Elon Musk. So I want to go over this narrative in a bit of detail, and I want to try to steelman it from an environmental and climate point of view, and just try to engage with it on its own terms as much as possible. So this is the best version of the argument in favor of this system that I've been able to come up with. So first of all, something we all agree on, private gas-burning automobiles are a major contributor to climate change. That has to change one way or another. That's the starting point, which I think anyone with any perspective on sustainable mobility is going to agree with. However, people are extremely set in their ways about their transportation habits. This is an extremely difficult system to change, both for sort of personal practice reasons, for cultural reasons, for infrastructural reasons, for political reasons. So people live in far-flung suburbs. We can't easily cram them all back into downtowns. That would cause gentrification, which is something an argument you often see in kind of the left-wing side of the defending cars kind of arguments. People have friends and families that now live far apart. That's going to be hard to change quickly. They need cars to visit them. Cars have become essential in many places to care for children. Now you can say that in some cases this is basically an arms race where you get a bigger and bigger tank to protect your kids from everyone else's tank, but that still has momentum and is hard to stop. Effective public transit infrastructure might be a good idea, but it will take decades to build. That's even if you have the political capital. And motorists vote, so do auto workers. The industry has political influence. All of this means that you have a big uphill battle to fight to actually challenge car dependence. So getting people out of their cars fast enough to deal with climate change would be extremely difficult. Therefore, we need an easier way, which is less contentious, less politically difficult, and asks less of ordinary travelers. So that easier way, there's a standard narrative for what that looks like. First, the current system is inefficient. But we can make it more efficient with shared autonomous vehicles, which will make shared mobility cheaper than driving a privately owned car. It means that you'll have the end of private car ownership, and due to economies of scale, these vehicles will be electric. The result will be massive improvements in safety, traffic efficiency, time use, land availability, and greenhouse gas emissions. And the process itself, according to this narrative, is self-driving. We just have to let car companies and tech firms do their thing, and this will all happen due to nice natural market forces. Obviously, I'm sprinkling plenty of sarcasm into this, but I'm trying to engage in good faith with the people who promote these ideas and trying to present the best version of this argument. One thing that I think is worth pointing out, and it plays into that 1950s depiction that I saw there, that I pointed out in the first slide. This is more automobility. This is like the current system we have, but more so, but also becomes sustainable, right? So that's part of the logic as well, that it takes that same kind of cultural, economic, political logic and just enhances it. At least that's the idea. Is it true? Well, we can point to a few objections. First, there's the obvious technical one. Self-driving cars are very far away. We probably can't build electric vehicles fast enough. Electric autonomous vehicles do nothing to reduce a lot of other problems: air pollution, urban sprawl, road deaths. Cars have embodied emissions. Autonomous driving technology seems very far off today, and there's actually very little evidence that people will prefer shared autonomous vehicles over private ones. But let's leave all that aside for a moment and give this the benefit of the doubt. I want to dig into the deeper question. If this works technically and environmentally, will it work politically in the way it's presented as? Will it be the sort of easy street? Well, for that, we need to talk about the political economic structure of car dependence. So some of you will recognize some of these diagrams from our paper that we published last year, I think came out. Yeah. So I break it down into three big categories of things that really lock in car dependence and that are stabilizing forces. There's the car industry, its size, its rigidity, the politics of land use, which is this kind of self-perpetuating feedback loop where more car-dependent land use creates demand for more cars, which in turn makes land use even more car-dependent. And that's locked in by various institutional and social and economic forces. And then there's car culture, which adds additional momentum to other developments and makes cars this highly symbolic good, which people feel a real obligation to own, even if they don't necessarily need it for practical reasons. But of course, on a cultural level, there are everyday life practices as well that demand cars. So, okay, the first thing I'm going to talk about with in connection to this is vehicle electrification and its political economic outlook. So there are three big things we can talk about that are different about electric vehicles. First, they have batteries and motors instead of engines, obviously. But what that means is that they're built differently. They require different infrastructure, different skills, different processes to be constructed. It's a lot of electrochemical engineering as opposed to steel stamping, which is how you build a conventional vehicle. They require different charging infrastructure. This, in many ways, is fundamentally different from conventional gas stations in ways that I'll get into in a minute. And they have fewer moving parts. This is actually critical because it reduces maintenance costs and increases the longevity of the vehicle. So what does that mean for the car industry? Well, in I think it was last year, one of the largest car plants in Canada, in Oshawa, Ontario, closed. It was a GM facility. And the stated reason GM gave was that they were pivoting to electric vehicles, and Oshawa was not part of that plan. And that's the thing about electric vehicle production, is that you can build an electric vehicle, you can convert a conventional vehicle factory into an electric vehicle factory, and that does happen. But it's also very easy to build an electric vehicle factory from scratch because the production infrastructure is different. That means that the concentration of the car industry worldwide is going to move around a little bit. And that removes the geographic advantage of places with existing car production capacity. So not all places that currently make internal combustion vehicles will make the transition. Places like Oshawa, heavily dependent on these car factories, could lose out. Turnover. Most evidence we have suggests that electric vehicles will last much, much longer than conventional vehicles. This reduces the rate of new vehicle sales, which is very bad for the financial model of the car industry. They need a minimum rate of new vehicle sales. And dealerships. Dealerships are a critical part of the industry. They rely on maintenance for over 50% of their revenue. Maintenance costs for electric vehicles are significantly less, so that revenue will fall. And that could critically threaten dealerships, which could critically threaten the industry's distribution model. And that is a reason why that we have seen, I think, some reluctance on the part of incumbent car manufacturers to switch to electric. In terms of electric vehicle infrastructure, there's some complex politics here. So here is a pickup truck, which this is extremely cringe-inducing. I identify as a Prius, deliberately blocking a Tesla charger. And this is called icing. This has been happening at electric vehicle infrastructure for a while now, all over the world. In fact, I've seen articles from China, Australia, Germany, obviously the United States.
Cameron, you froze just a bit. You froze just a bit. Can you repeat after
okay,
Germany?
Yeah, well, so it's happened in Germany, Australia, the United States. It's a global phenomenon of people deliberately blocking charging infrastructure, often as a kind of resentment about the space it takes up and the parking spaces they can no longer access. Fights over parking have already, and a huge addition to electric vehicles will require curbside parking spaces to be reserved for charging. Curb space is already a scarce and politically contested resource in cities. That's why we see so much fighting around bike lanes. And I think there could be a real comparison between mass construction of charge points and mass construction of bike lanes. There is a plus side. There are more private businesses that could benefit from electric vehicle charging that couldn't benefit from a gas station. The final thing is culture. So here's some culturally laden imagery. People have been stuffing meat into electric vehicle charging stations. I'll let you read what other symbolism you want into that, but I'm pretty sure there is plenty. I think electric vehicles' compatibility with existing cultural narratives of automobility is mixed. They have had some successes here, but only among certain cultural groups, certain subcultures. I think we're still very much, I don't like this model of technology diffusion, but in this case, it kind of serves my purposes. I think we're very much sort of in the early adopter phase, early majority still. The people on this end of the graph, they are going to have objections that we have not seen en masse yet. Electric vehicle adoption is predominantly in a small subset of society, and their cultural compatibility might be more strained as they start to be adopted by other groups. So I'm going to move on fairly quickly here to autonomous vehicles. So there's a lot of wide-ranging estimates of the impacts of autonomous vehicles on emissions and travel behavior. It's mainly in the positive. It's mainly going to increase energy vehicle kilometers traveled. But the solution that's typically proposed to get these positive scenarios is policy tinkering. You just need the right policy and autonomous vehicles will be fine and beneficial. The problem is that the history of transportation policy has not been guided by this kind of rational policy engineering approach. Historically, politics of major transportation transitions have not been characterized by a rational evidence-based approach to problem solving. Our current political consensus on transportation was the result of literal street battles. Why would we expect this to be any different? And based on some of the history I've looked at here, I can talk about three big historic tensions in transportation politics. So there's the rights to access and use of infrastructure, provision of resources, money, labor, natural resources, land, and the responsibility for unintended consequences. So pollution, deaths and injuries, and aesthetic blights. These are often foisted onto the groups with the least political power. So currently we have a transportation consensus that's almost a century old now. It came about from the 1920s. Basically, all motorists have roughly equal status and equal access to infrastructure. Of course, there's a big asterisk there for various race and class issues, which are outside of my scope here, but I do need to point them out. Roads are primarily for motorists, so they're not, for example, for protesters in some places. Other users might be permitted, but only on specific conditions. They may have to deal with hostility. For people who don't or can't drive, a patchwork of alternatives is provided, i.e. public transit, but the quality does not have to be high. For infrastructure, the government will provide road infrastructure for motorists that will, for the most part, be free at the point of use. Unintended consequences will be mitigated somewhat by systems of licensing, insurance, and policing. So what does this mean for autonomous vehicles? Well, for traffic efficiency and safety benefits of this technology to materialize, a huge majority of vehicles need to be both autonomous and networked. There are already concerns that and that means that you need to actually push non-autonomous vehicles off of the road. Implications for pedestrians and cyclists are particularly unclear here. There are concerns that they might take advantage of autonomous vehicles' safety to jaywalk more aggressively. There have been suggestions of segregated lanes, outright bans of non-autonomous vehicles, and there's a lot of possible avenues for opposition here. I won't read them all out in detail, but I'm sure you can think of where those fights might come from. The important point here is that this realigns some of the political factions, and I have a diagram about that in a second. For the cost of infrastructure, the integrating autonomous vehicles into the system will have major costs in finance, land, resources. The benefits of these will initially accrue primarily to wealthier people who can afford autonomous cars. And it will impact the resources available to other systems. So for example, public transit could find itself badly outcompeted by shared autonomous vehicles. Municipal parking revenue, if people are just sending their cars to park where it's cheaper autonomously. A lot of cities depend critically on parking revenue for basic finances. Insurance revenue to pay for the cost of collisions. This will disrupt the insurance system in a major way. And there's already been suggestions of funding this with a bid-based intersection model. There are several computer science papers based on this where you automatically bid real money for the right to pass through an intersection. And that's how the intersection will be managed in terms of priority. So obviously, rich people go first. So automobility has always been a system that blends public and private provision of mobility, but this would sort of scramble that and change the structure of it, creating different classes of road users competing for the same pool of resources. Finally, there are unintended consequences, and this is the classic ethics problem of how ethical your autonomous car should be. Most people want autonomous cars to be altruistic, except for the one they themselves are traveling in, which they want to be selfish. So this is a collective action problem, which requires a policy response, but that leads to issues. We already have in the world today radar detectors, right, as a way of getting out of speed traps. And there's no reason to think that people wouldn't tinker with the ethics settings on their autonomous cars using, say, aftermarket modifications. There are also huge unsolved legal problems here about liability for accidents, and that's going to be settled in some very contentious case law. So I'm not going to go over every detail here, but I've broken down all of the big debates about what to do over autonomous vehicles into different kinds of policy measures that might happen, what the knock-on impacts of these might be, and what further policy measures might then be required. And then the proponents of these that might emerge. And I will share this line. I just want to do a sort of back of the envelope coalition analysis here. So this is the incumbent automobility system. And the reason it's so stable is because the coalition supporting it is pretty big. We have motorists, traffic engineers, truck and bus companies, oil companies, wealthy people, people who are just ideologically individualist, infrastructure companies, construction, car manufacturers. And then opposing it, we have a fairly scattered coalition of environmentalists, pedestrians and cyclists, and transit users who don't have a lot of power. What does it look like in the fight over autonomous vehicles? Well, it's a lot more balanced. Suddenly, we have traditional motorists who might not want an autonomous car, critics of public spending. Individualists will suddenly be much more opposed. Civil libertarians, a lot of less wealthy people, will suddenly enter a coalition that opposes this change. Meanwhile, there will be a coalition that involves technophiles. Insurance companies will probably support it, supporting autonomous vehicles. And so what that means is that the politics is about to get a lot more contentious. And we've seen what that looks like. We've seen that historically that gets messy, that these political consensus around transportation are very hard fought. And so I think it's unrealistic to think that we're going to get a kind of sensible policy deliberation to get the rational best outcome from this technology. So to conclude, this is basically the vision of electric autonomous mobility as this nice, efficient transportation system. You Google this, there are a million diagrams of this, but we've seen this before, right? This is Futurama in the year 1940 1940, I believe, in New York City, this was what people thought interstate highways would look like. Obviously, they didn't. The car industry and car culture has a long history of these kinds of technocratic visions of how they will solve all the problems with the next great techno and infrastructural complex. I think we should be skeptical. So I think the notion that electric and autonomous vehicles present an easy politics-free answer is false. I think they will trigger a lot of the same immune response from automobility, or the basic political and the transportation system that has lasted for most of the last century. So I know it's a bit scattered at this point, but the general point is that we shouldn't so easily accept that, even if we accept all the technical and environmental arguments, that this is the easy option compared to, say, just working on bike lanes, public transit, walkable communities, etc. And with that, I'm done. So I'm sorry I went over time, but I'm happy to take questions and discussion at this point.
So I'm Joel Millward-Hopkins. I've been on the LiLi project for a couple of years, and I'm particularly interested in inequality and energy, which is going to show today. So I've called this the energy requirements of providing universal decent living in a fairly unequal world, leaving fairly open to interpretations, which I'll come to soon. So I need to, okay, there we go. So in order to describe, well, yeah, in order to introduce what I'm going to do today, I'm going to have to first go over some previous work, which all of you are going to be familiar with, which is this decent living energy model. So first of all, I'm going to give a very brief primer on that, describing bottom-up versus top-down modeling. What are the decent living standards that we assume underpinning this model? And then three of the key assumptions we made in that model, which the work I've been doing recently kind of extends upon or criticizes. Then I'll go on to explain this extended model, which largely involves building inequalities into this decent living energy model, and seeing what the impacts are on global energy requirements. And I'll also briefly, without going into too much detail, briefly go over how I've implemented these inequalities, in particular this concept of fair inequalities and the kind of the sorts of notions of fairness that come out of public surveys on people's attitude to inequality. And then I'll move on to some results, mainly looking at the global energy costs of inequality in the context, or at least in relation to typical drivers of population and technology. Then I'll look at energy inequality in a bit more detail, and then probably very briefly go over some sectoral and regional outputs, because I don't think they're quite as interesting. Okay, so to begin with, just to refresh on this DLE model. So the first thing to note is this is very much a utopian, well, to some people, but it's very much a visionary model, and it's not a forecast. It's more of an exercise in seeing what is technologically possible, and technologically possible on the one hand, and possible from the perspective of basic human needs on the other. So the overarching question of that model was, how much energy does it take to provide decent living standards to a 10 billion population in 2050 with minimum energy use? I made this presentation on a computer without the internet, which explains the horrendous stigma. That's apparently what I think people look like. Anyway, so the second point is that the model is bottom up rather than top down. And essentially this means, instead of looking at statistical relationships in observed data, so relationships between impacts such as energy footprint, material use, carbon emissions, and social outcomes like life expectancy, etc. We're instead taking this very explicitly normative approach, where we say, what do we believe are the material prerequisites or requirements for a good life? And then we're looking at what are the minimum energy requirements of providing all of that. So what this means is we avoid this kind of issue of our results being contingent on current socio-political systems, which is implicit in looking at observed data, but also we end up with this kind of less practical and a bit more abstract model. And it's also, we're very much biased towards underestimating energy needs, because when you're looking at this material basis for a good life, you're far more likely to miss things out. So in the DLE model, for example, occasionally I just notice something that's missed out. So I realize there's no toothbrushes in there. We've got this world of decent living energy, but no one's got a toothbrush. Also, there's no furniture. But anyway, so we do tend towards underestimation. But then at the same time, we have covered all these really major parts of the material basis of a good life. So just to go over those decent living standards very briefly again, we have kind of 8 dimensions here. This is from Narasimha Rao's work. And then among these 8 different dimensions, there are various different sub-dimensions of material requirements. So for example, we have, obviously for nutrition, you've got food itself, you've got cooking appliances, and you've got cold storage for that food. If we go down to hygiene, we have water supply, some proportion of that that's heated, and then waste management services and toothbrushes, if I thought of that, and various other things. And then healthcare and education, we just have universal services. So that's probably enough for that. Now, these are the 3 really key overarching kind of large-scale assumptions of the DLE model. One being that we had inequalities only to the degree that they could be justified by need. So countries with sparser populations had more mobility. Countries in particularly hot or particularly cold climates had more energy use for thermal comfort at home. But beyond those need-based inequalities, there is basically perfect equality. So in the other way to look at that is this kind of equality in energy services, you could say. Then the second assumption that was very important is we're assuming really state-of-the-art technologies everywhere for everyone. So that's globally in 2050 for the whole world population, which is pretty ambitious by anyone's standards. And then finally, we assumed a population following the United Nations central projection, which if you look at other literature, that's actually pretty high. The UN's projection is close to 10 billion in 2050. And then when you start to look into the literature of what population might be if you start doing pretty well on the sustainable development goals related to education, gender equality, and health related to contraception access, then you start to see population coming down to like much closer to 8 billion. So the other way to look at this is the first of our 2 assumptions here mean that we had particularly low energy use. The third one actually pushed our energy use up a fair bit higher than might be considered reasonable. So in this work, I've been developing 6 more scenarios to kind of to play with these 3 assumptions essentially and question them. So the scenario 1 at the top of here, this is where the notation might get a bit confusing. So in the previous published work was called the Decent Living Energy Model. I've now called our kind of baseline scenario the Decent Living Energy Scenario, and it is essentially the same as the published DLE model. It has this state-of-the-art technologies everywhere. Inequalities between and within countries are both need-based only. And that means the lowest consumers are essentially the highest consumers as well, and they're all at these decent living standards. The only difference between this and the published model is we have this, I've been using a lower population trajectory. SSP1 is from the IPCC, and that's just their most sustainable scenario. And that comes up with just under 8.5 billion in 2050, which is a lot lower than we used before, obviously. So then for comparison, the next scenario is just a very simple change to that base DLE scenario when I change the population to SSP3 from the IPCC, which is about 10 billion by 2050, which essentially means this high population scenario is just about the same as the published DLE model. Then I have a current technology scenario. That's again the same as the DLE scenario, but now there's just a modification made to technology. So instead of having these state-of-the-art technologies everywhere, I've called this current best practice, but there's essentially just a small reduction in our technological ambition. It's probably easier to describe through examples. So in the state-of-the-art technology scenario, I will have really advanced buildings everywhere, which are near passive. And in this current best practice, I've used energy intensities, which are kind of closer to a deep retrofit or a moderately advanced new building in the terminology of the data source. I guess ironically for vehicles, for the state of the art assumptions, I've got partially automated, very efficient electric cars. And then in the current best practice, I'm using kind of efficiencies based upon widely sold but efficient electric cars today. So that hopefully gives some context of the difference between those two. But then the most important three scenarios, these final three. So these are where I start to implement inequality into the model. So the first one, I've been using this notion of fair inequality, derived based upon these public surveys of public notions of fairness, basically public notions of what a fair society looks like in economic terms or in income terms. So this fair inequality scenario ends up being the same as the decent living energy scenario in terms of population and technology, and in terms of inequality between countries. But then within countries, I've added this inequality to the degree that people believe inequality is fair. And then also the key point here is as well, people at the bottom of the distribution are always kept at decent living standards. So when inequality is added in, that means some people are brought up, but no one is brought down. So then in this super rich scenario, that's the same as this fair inequality scenario, except for the very top 1% of the population in each country. And I've then basically put them right up to be roughly in line with the super rich today on some kind of key categories, so mobility and housing size, for example. And then finally, I have this fairly large inequality scenario, where I've just increased inequality within countries to be roughly within the range you might find today in more equal countries. Specifically, I have Gini coefficients between about 0.25 and 0.45. But actually, because of the way I've implemented inequality, it's kind of hard to actually get a real hook on what that means. So I guess I can leave questions about methodology to the end, but I'll try not to go over too much of it now because it's a bit distracting. Oh yeah, final point. All the estimates are static estimates and they're for the year 2050. And by static, that means that we include the energy use of all infrastructure, but it's divided over the lifetime of that infrastructure, and the same for products. So if you have like household appliances, the embodied energy of those household appliances is included, but it's divided by 15 or 20 years or however long they last. So this is the one slide I'll go over to indicate the methodology, because I kind of need to explain why these figures are going to be step shaped like this. So in the previous model for fair inequalities, or the previous paper that me and Yannick have published, we looked at this notion of fair economic inequality and what that would mean for carbon footprints. And we developed these three simple kind of stylized distributions for different country types. So where countries seem to have a low preference or preference for low income inequalities, we developed this simple distribution along the bottom, which basically says the lowest 10% of the population here. I've just got relative consumption on the axis here rather than income. So the lowest 10% are kind of at the decent living standards. And then as you go up the distribution to the very top 1%, their relative consumption is about 2.5 times those at the bottom. So then we have countries where they have sort of a moderate preference for inequalities, and then meritocratic countries. I've called the countries where their preference for, or their notions of fairness are particularly high income ratios. And then we end up with these different, basically very similarly stepped three stylized distributions. I hope that makes some sense, but to try and clarify a bit more, this figure on the right is for the UK. And the UK comes out as a meritocratic country. Like people, I think the average of surveys is people think an income ratio of 6 is about fair. So they think it's fair if the richest people in society have about 6 times the income of the lowest or the unskilled in the terms of the survey. So what that means when I implement that into the decent living standards is for residential floor space, for example, decent living standards are about 15 meters squared per person. So if you implement this notion of fair inequalities, you end up with, as you move through the population, there's more floor space until you get to the top 1%, which are houses about 8 times larger than this bottom 10%. For private road transport, the pattern is about the same, but because I'm only applying inequalities to key kind of private consumption categories, total mobility is a bit flatter. So I'm not assuming that wealthier people take more, not assuming that wealthier people use more public transport. There's a displacement effect instead. So as they drive more, there's less public transport, which means that overall mobility isn't quite as unevenly distributed as this stylized distribution. So with all that in mind, these are the key outputs for total global energy use. So the decent living energy scenario. So these are the 6 scenarios from the table. So this new decent living energy scenario is down here, about 125 exajoules per year, which is a lot lower than current levels, as I'll come to in a second. If you go from this low population scenario to about the highest population that anyone's projecting in 2050, you get about an 18% increase in the energy requirements for providing universal decent living, which is significant, but in context, not particularly much. If you decrease the technological ambition from this state-of-the-art everywhere assumption to current technologies, the increase is nearly 50%, which is pretty large considering that conceptually those 2 scenarios aren't that different. Even in this current technology scenario, we're assuming pretty high efficiency technologies everywhere. My mouse is disappearing. And if we move on to these fair inequality and super rich scenarios, then they're round about the same as the current technology scenario. So you're looking at something like a 40 to 60% increase in emissions over this DLE scenario with perfect equality. So what this essentially means is even the energy costs of inequality, if you like, even in the case where inequalities are kept between those levels people think are fair, are pretty substantial. Fair inequalities increase global energy use to provide universal decent living by about twice as much as going from the lowest to highest population trajectories do. The change from the fair inequality to the super rich scenario, which, just to refresh, this difference here is purely due to the top 1% increasing their consumption from the levels in this fair inequality scenario, which are already relatively high up until kind of these roughly the levels of the super rich today. And that increase there is also the same again as the increase from the low to high population trajectories. And then if you go to inequalities which are slightly more in line today, so this fairly large inequality scenario, then you end up with your energy required for universal decent living is actually doubling, which is pretty significant. Especially when you consider, if I went back to that table, in all these scenarios, there's no inequalities between nations, apart from those based upon need. So the inequality in all these 3 scenarios is much, much lower than you'll find today, essentially. So to put this into context, on the right, instead of just plotting them all on the same figure, which would make these differences look a bit too small, I've plotted the DLE scenario versus some projections from the IEA for 2050, and these are the 2 most ambitious projections of the IEA. So they have a couple of scenarios which are one's called the Sustainable Development Scenario, one the Net Zero by 2050 scenario. So these are both very ambitious scenarios, and they project in between 350 and 400 exajoules by 2050. So you're looking at about yeah, about 3 times the DLE estimate, essentially. The IPCC energy use, even in their 1.5 degrees compliant scenarios, is really, really high, anything from 250 to well above 500 exajoules in 2050. The only way I can make the decent living energy model get anywhere near those values is by combining all these assumptions of all the 6 scenarios. So if I take a high population, current technologies, and implement these fairly large inequalities, then I end up with a little over 400 exajoules, which puts me about in the middle of the IPCC range. But the key thing here is both the IEA and the IPCC are very often relying on lots of negative emissions and various other assumptions which are quite contentious. So moving on to look at energy inequality in a bit more detail. These are the 3 inequality scenarios plotted in the 3 shades of orange. And this is now we're looking at energy use per person, and looking at that across the full range of basically low to high consumers. So down here,
Joel, I was thinking the last slide was the last one, but we're coming up to 4 p.m. UK time.
This will do for the last one. Don't need to pretend you need to. Yeah, maybe I'll just try and go through this very quickly. So in terms of per person emissions, down here at decent living standards, in all 3 of these inequality scenarios, you're looking at just under 15 gigajoules per year per person, which is roughly the same as national averages in India and Tanzania and Ethiopia now. So these fairly low consuming global south countries, where obviously they're at these energy levels now, and clearly decent living standards aren't met by any means universally. If you move to the upper 1% in this fair inequality scenario, there the output is 37 gigajoules per capita, which is about the same as the bottom 20% in global north countries like Germany, Italy, and Japan. So essentially your highest consumers in this fair inequality scenario are still very low by global standards now, or definitely by global north standards. In this fairly large inequality scenario, the upper 1% end up a little bit higher than these global north countries' national averages. So Germany, Italy, and Japan are in the range of 65 and 85. And finally, going up to the super rich scenario, where I've just increased the very upper 1% of this fair inequality scenario. That's when you start to see energy use really in line with kind of the richest part of the population in the richest nations today, like the USA. So I think I will leave it there then.